Okay, so welcome back, and we were discussing about stresses and strains in individual elements of a component. So we saw that even though you may start with an element has only normal stresses, but if you rotate the element you can have normal as well as shear stresses. Now we said that the inverse is also possible, where you can have a combination of normal and shear stresses, but you can rotate it to a position where you have now only normal stresses, and these are called, remember what we talked about, these are called principal stresses. So we were talking about principal stresses. A condition on an element where you have normal plus shear, and if you rotate particular angle, and that you will be able to find when we discuss about Mohr circle. So when you rotate you will get to a position where you have only normal stresses. And this is what we call as principal stresses. So if you were to understand it pictorially, you can say that we start, let us take the element in a, this is a small element, infinitesimally small element inside a component. So you have stresses like this, so remember this is trying to rotate it clockwise, these two are trying to rotate it anti-clockwise, and these two must be the magnitude of this must be equal to the magnitude of this, because the element is in equilibrium. Now if you, so here we have both normal and shear stresses. Now let us say for a particular rotation, in this case let us say after rotation of 45 degrees we end up having stresses like this. Then here you can see there you have only normal stresses, you do not have any shear stresses, and in that case whatever the values of these two normal stresses, there are two normal stresses, we are talking in 2D, 2 dimension. So here you will have two principal stresses, and one will be called sigma 1, other will be called sigma 2, and the convention that we follow is that you will give value sigma 1 to the one which is highest, then sigma 2 which is second lowest, and in case we are talking in 3 dimensions you will have 3 principal stresses and it will be called sigma 3. So we see these that there can be up to 3 principal stresses, and in 2 dimension it will be 2 principal stresses, and when the principal stresses exist there will be no shear stresses inside on that particular component. So it is at that particular angle, and you will be able to see when we use what is called as Mohr circle construction, that you can see that there will exist a particular rotation for which you will have no shear stresses and only normal stresses, and you will also see that in general there will not be, you cannot say that there will also be a position where there will only be shear stresses and there will be no normal stresses. In particular cases it can be, but in general that will not be true. Now once you know what are these principal stresses, it is now time to look at some equation. Again, do not get bogged down by these equations. These equations I am showing over here just for sake of completeness. So how do we find these principal stresses? Let us say you have a particular condition where you are able to get sigma x, sigma y, sigma z, sigma xy, sigma yx and sigma zx, and all those parameters or all those stresses, the 6 components, then you would be able to find these principal stresses using this equation, where this is the unknown quantity of or the roots of this will give you the value I1 is actually called the stress invariant I1, I2 stress invariant 2 times sigma p minus I3. So, you see this is the cubic equation where sigma p is your unknown and the roots, when you solve this, the values that you get will give you sigma 1, sigma 2 and sigma 3. And if we are talking about 2 dimension, then this will get reduced automatically to a quadratic equation and you will get only 2 values. And here I1, I2, I3 are the values where, or the invariants which are called the stress invariants, or where you will put in the values or from the known parameters or the known stress values. So, I1 is given as sigma xx plus sigma yy plus sigma zz. Sigma x I2 stress invariant sigma 2 I2 is given as sigma xy square plus sigma yz square plus sigma zx square minus sigma xx sigma yy, no, sorry, this is minus and again minus sigma xx sigma yz square this is not a z square, this is xx. So, we had xx and yy. So, here we will have yy and zz, sorry, please make that correction. So, this is yy, I went ahead for I3, it is I2. So, in I2 we have minus sigma xx sigma yy minus sigma yy sigma zz and minus sigma zz sigma xx. This is I2 and you have I3 which is given as sigma zz plus 2 sigma xy So, we have I1, I2, I3. Now, what you will see is that this is your I1. Now, if you left for particular condition, you will know sigma xx, sigma yy, sigma zz and you will also know sigma xy, sigma yz and sigma zx. So, once you know all those values, you can just insert it here to get I1. Now, you would think that if you start with a different rotation, you may get different values of sigma xx, sigma yy and sigma zz. In that case, you would get different values of I1, I2, I3. And when you insert it over here, you should get different principal stresses, although the element remains the same and the sigma p or the principal stresses should come out to be the same value. But that is why we call it stress invariant. No matter what particular orientation of the element you take, when you take these values for that particular element in that particular orientation, the sum of these would come out to a value which is constant. So, no matter how much you rotate it, as long as you are at the same element, this value will not change. So, the combination, the 3 can vary, but the sum of these combinations will always come out to be constant, and that is why it is called invariant. Similarly for I2 and similarly for I3, and once you put all those 3 over here, you can see you will get same principal stresses for that particular element. Now, this is trying to find out principal stresses using this equation, but we have another formalism or construct what is called as Mohr circle construction. This is a very interesting way to find out the values of the values of principal stresses. So, let us say we take two axes where your x axis represents normal stresses and your y axis represents shear stresses. Now, let us say you take a biaxial stress condition where you have only where you have a particular stress condition which will show like this. Let us say now you have sigma xx which is given by some positive value and you have some sigma yy value which is negative. So, you plot this sigma xx, and on that particular plane you also have a shear value. So, you will be able to plot a shear value for this, and similarly you will have a shear value for sigma yy, and we know it, and right now we are taking a 2-dimensional case. So, if I were to draw this, so this is our xx, in x we have positive, so this is tensile, here we have compressive. So, this is the element we are talking about, this is sigma xx, this is sigma yy, and this is sigma xy. So, this is trying to rotate it clockwise and equal in magnitude, but opposite in direction. What we have is sigma yx. This is trying to rotate it anti-clockwise. So, this is sigma xx on the x axis, and on the y axis we have sigma xy. Over here we have sigma yy, and on the y axis we have minus sigma xy, or which is equal to sigma yx. So, this is a sigma yy value, this is a sigma xx value. Now, when you plot these 2 points over here, right now do not think that I have drawn a circle. Okay. So, the circle comes later. Once you have these 2 points and taking this to be a diameter, now if you draw a circle, this is what is called a Mohr circle for this particular element, and let us say this is the center. So, now all you need to do to find the principal stresses is look at the values on the x axis. So, over here this gives you sigma 1, and since we are talking in 2 dimension, we have only 2 principal stresses, sigma 1 and sigma 2. So, once you were in a position to put these 2 points on this 2-dimensional map, you have x and y coordinates, you have x and y coordinates at this place, you are able to draw a circle assuming these 2 points to be the diameter. And once you have this circle, the circle wherever it intersects the x axis, those 2 points are what gives you the principal stresses. So, this is a very simple geometric construction and technique to find out the principal stresses. You do not have to go through all that complicated mathematics. So, that is why I said do not get intimidated by looking at the equations. If you there are simpler ways, but for the sake of completeness we have put in all those equations, and there are simpler ways like this one to find out the principal stresses. And in many cases when you are dealing with our some of the deformation techniques, we do not even need to find each and every components, like even principal stresses. Most of the time we have simplified it further, as you will see later on, so that you can deal with just one number. You do not have to deal with all the 7 parameters, or even in case of 2 dimension you do not have to deal with 4 parameters. Another thing that you should realize from this is that when you have a clockwise shear movement, then that is given as positive value. So, here the shear is positive. If you look at sigma xy and sigma xy over here, it is clockwise, and clockwise is related to positive value. On the other hand, sigma yx is anti-clockwise, and that is related to negative value. So, you see sigma yx is same in magnitude as sigma xy, but it is on the positive y axis and this is on the negative y axis. For the tensile and compression or the normal stresses, when we are talking about tensile stresses, it is positive. So, sigma 1, as you can see in this particular case, comes out to be positive, and sigma 2 in this case comes out to be negative. Similarly, sigma xx, which is tensile, is plotted as positive, and sigma yy, which is compression, is plotted as negative value over here. So, these are some of the things that you should understand that go along with Mohr circle, and to put it in perspective, or to put it formalize it, let us write down what are the things that we can find out as a result of Mohr circle. So, we can find out plane orientation. We can find out principal stresses from this. We also see one important thing that I have been telling you so far is that there exists a particular orientation. So, you see we had this orientation to begin with, but if we rotate it by some angle which will also imply a rotation on this particular plane, we will get to a particular orientation where you have only normal stresses. You remember, this is why we are calling these as principal stresses. So, when we rotate it by a particular angle, we do get to a position where we have only normal stresses and no shear stresses. So, there exists a no shear stress orientation. But how much do we need to rotate when we rotate by some angle? Let us say if I see over here that this has to be rotated by 2 theta, and there is a reason why I am writing it as 2 theta and not as theta. How much should the actual element be rotated by? Okay, now we have not gone into the equation, and so I will simply put it here in words that if you want to go to 2 theta in the Mohr circle, then you have to rotate your element by half of that angle. So, you will have to rotate it by theta. So, this is going this is going clockwise. So, here you will go clockwise. So, this is your theta. So, in other words, when you rotate on the element by angle theta, on the Mohr circle it gets rotated by 2 theta. So, there is rotation on element by theta leads to rotation on Mohr circle by 2 theta. And just now I noticed that I mistakenly have called this as anti-clockwise. Actually this is clockwise. So, right, I was right, okay. So, do not worry about that. So, these are some of the things that we can extract from Mohr circle. Now, another thing that you would see is that we said that there exists a no shear stress orientation. Do we see a no normal stress orientation over here? What will be the condition where you will have no normal stress? So, one of these would have to be here and the other will have to be over here. But if you take this as the diameter, it will be a completely new circle. So, if we are talking about this same element, okay, so remember this one circle represents one element. Here we can rotate it and it means we are rotating the same element or at the same point inside the component. But if we draw a new circle over here, it would represent a new element or a different element on the component. So, we cannot take these 2 points for this same element, but there may of course exist some elements where this and this will be your stresses, sigma xx and sigma yy. However, for this particular element that there does not exist a particular orientation where you can get only shear stresses and non-normal stresses. We will get to a simple Mohr circle for that too, for certain cases where you can get elements like that. Now, before we move on, let us look at one of the example that not example, but we talked about a case where we rotated earlier, we were rotating the element by certain angle and we saw that at 90 degree there did not exist either a normal stress or a shear stress. Remember, so we were talking about it in the previous lecture. Now, if we were to look at such a particular condition, which it is nothing but a simple tensile or compressive behavior. So, a Mohr circle which represents just one principal stress, or basically where only to begin with in the normal element we have only one principal stress. So, you remember in this particular case, since we were talking about so there was some weight that was going on to this. So, this is compressive. Okay. So, okay, let me be consistent and let me draw just the compressive part. So, if I have to draw the compressive, it means the principal stress would be on the negative side. So, this is, so my circle is on the left side of my y axis, because we are talking about compressive stresses. So, this is your y axis, this is a positive x axis, and on the negative x axis we have the stress. And when we look at the element just like that, that is in the normal condition, we have stresses acting on it, where sigma W is the force and A is the normal area. So, stress equal to W by A. So, this was the stress acting on it, and there are no other stresses in perpendicular directions. So, this is represented as this sigma naught, which is our sigma actually 3. Why I am calling 3? Because sigma 1, which is 0, is higher or larger in magnitude than sigma 3. This is a negative quantity. So, this becomes our sigma 1, which is equal to 0, and sigma 2 is of course also 0. So, we have sigma 1 equal to 0, sigma 2 equal to 0, and sigma 3 equal to sigma naught, which is a negative quantity. Now, in this particular case, when we rotate it by 90 degrees, we had taken a different plane from this normal. So, this was theta, and we said that if you take theta equal to 90 degrees, which means over here, if this is the circle, you are rotating a line by 2 theta, which means you are doing nothing but you are rotating it by 180 degrees, and therefore, this sigma that we were trying to calculate is 0, shear stress is 0, but that does not mean there does not exist any principal stress. If you look at 90 degrees from this, that is, there is a normal stress, like this, and there, since this is an element, there is also a normal stress like this. So, if you look at the normal stress at 90 degrees from it, there still exists this value. Okay. So, we are looking, in fact, if you look at it carefully, what we are saying is that our original element, which existed like this, has been rotated by 90 degrees. So, what was sigma 1, this was sigma 3. Now, where the sigma 1 should have existed, now there exists sigma 1. Where sigma 3 should exist, there exists sigma 1. So, this is what happened when we rotated this by 90 degrees. So, this is the example of Mohr circle, where we have now seen a general condition where you have sigma xx, sigma xy, sigma yy and sigma yx, and where we have looked at a simple compressive stress. Now, tell me, how will it be different when you are talking about uniaxial tensile condition? How should this Mohr circle look like? You must have gotten a pretty good idea by now, because what we drew here was uniaxial compression. So, if you want to draw a uniaxial tensile stress condition, Mohr circle for a uniaxial tensile condition, it will be like this. It is the same circle, but now it exists in the positive x axis. On y axis it is symmetric, so it does not matter, because y axis it has y axis, why does it have to be symmetric? Because tau xy has to be equal to tau yx in magnitude, and sign they have to be opposite, one will be clockwise, the other will be anti-clockwise. So, if we look at the tensile condition, so these 2 points represent the principal stresses. So, let us say I have so this sigma naught is actually equal to sigma 1 and sigma 2 and sigma 3 in the perpendicular directions are all equal to 0. So, this becomes sigma 1, this becomes sigma 2 equal to sigma 3 equal to 0. And in this particular case, in this particular orientation, if you take any element inside this gauge area, that element is only exposed to normal stress and there are no shear stresses, which is what is reflected by this diameter. One principal stress, the other principal stress, and these two do not have, or the component y axis component for both of them is 0. So, there does not exist any shear stress. So, this is the condition for uniaxial tensile. However, if you take an element over here and look at it in a different orientation. So, instead of now looking at it in the same orientation as the stresses, now let me take a orientation of an element in a little bit different direction. Okay. So, now you see this is a little bit rotated, I have rotated it by clockwise by some angle, let us say theta. What will that imply? The stresses on that particular element will now be given by a diameter which is now rotated from this original one by angle 2 theta. So, this will be your sigma x comma sigma xy, this will be your sigma y comma sigma yx. And just from looking at this, I can say that sigma xy is negative. It means if this is, if I am calling this as sigma x, then sigma xy is negative, it implies it must be in anti-clockwise direction. So, this sigma xy must be like this. On the other hand, sigma yx is positive. So, if this is my sigma y, the sigma xy, the sigma yx is sigma y and this is sigma yx must be in clockwise because sigma yx is positive. And both my sigma y and sigma x are positive. So, both of them are in tensile condition. So, this sigma x as you see is positive, this is sigma y which is again positive. So, we are able to get or extract so much information from this Mohr circle just by looking at it, and by simple construction we are able to not only get the stress conditions or the stress values at different orientation, but also their magnitude, their sign, and we can also work it backwards when we have a condition where of normal stresses plus mixed stresses for plus shear stresses, we are able to get back to the principal stresses. So, we will look at one more example of Mohr circle when we meet in the next lecture. So, we will end at this point and we will come back next time. Okay, thanks.